See, the formula of self-induction is, we did in the last class, mu naught pi r square n square L, where n is number of turns per unit length. L is given to be 50 centimeter, which is basically 50 into 10 raised to the power minus 2 meter. The radius of the coil is 2 centimeter, which is basically 2 into 10 raised to the power minus 2 meter. So small n is number of turns per unit length. It's total number of turns divided by length, total length. So the total number of turns are 500. The total length is 50 centimeter. So that's basically 50 into 10 raised to the power minus 2. So if I cancel this, this comes out to be 10. That's 10 raised to the power 3 turns per meter. So if I substitute all values here, then L is its mu naught, which is 4 pi into 10 raised to the power minus 7 into pi, which is 3.14, r square, which is 2 into 10 raised to the power minus 2 square, into n square, which is 10 raised to the power 3 square, multiplied by L. L is 50 into 10 raised to the power minus 2. So that self-induction comes out to be, that's 4 pi. Say pi into pi is 9.8, which is all, this into this is almost 10. Pi into pi comes out to be 9.8, which is basically equal to 10. So that comes to be 40 into 10 raised to the power minus 7. This is 2 into 10 raised power minus 2, which is 4 into 10 raised to the power minus 4. 10 raised power 6 multiplied by 50 into 10 raised to the power minus 2. So now this is 40 into 4 into 50. So this is 520, 80 into 10 raised to the power. Minus 7, minus 4, minus 11. Minus 11 and 6, minus 5. Minus 5 and 1, minus 4. Minus 4 and minus 2, minus 6. So your self-inductance is 8 into 10 raised to the power minus 600. So just one more question on self-induction, then we'll start calculating energy. So if you want hint for this numerical, for induced EMF, you can use this relation minus L di over dt. You have enough data to calculate di over dt, say. So this is your initial current. Your final current is 0 because switched is off. The time is 10 raised to minus. Instead of di over dt, you can write this as delta I over delta. For L, you can use this relation, the relation that we have derived yesterday, like mu naught n square pi r square. So if I take small n, that's total number of turns by length, which is 500 divided by total length, that's basically 30 centimeter, which is 0.3 meter. So the number of turns per unit length is 5000 by 3 per meter. That's small. This pi r square area is basically 25 centimeter square. It's 25 into 10 raised to the power minus 4 meter square. Length is 30 centimeter, which is basically 0.3 meter. So if I substitute all values here, your mu naught comes out to be 4 pi into 10 raised to the power minus 7. It's n square, so that's 5000 by 3 square. 5000 by 3 square into pi r square. which is 25 into 10 raised to the power minus 4 multiplied by L, which is 0.30. So this is 25 into 4, it's 100 pi into 10 raised to the power minus 7 into minus 4, it's minus 11. 5,000 by 3 square. So that's 25 into 10 raised to the power 6 by 9 multiplied by 0.3. So your L comes out to be 25 into 0.3 by 9 pi into 10 raised to the power 6 minus 11 and 6. So that is minus 5 plus 2 minus 3. Now, if I have L and this is delta I by delta T. So delta I is final current minus initial current. Finally, your current is 0. Initially, it's 2.5. So the current is minus of 2.5. Time interval, the current is getting 0 and 10 raised to power minus 3 seconds. So delta T is minus 3 seconds. So if I substitute all values here, if I substitute all these numbers here, your EMF will comes out to be minus of L, which is 25 into 0.3 pi by 9 into 10 raised to the power minus 3 multiplied by minus of 2.5 by 10 raised to the power minus 3. So this 10 raised to the power minus 3 will cancel this 10 raised to the power minus 3. So you are left with just your E is, it's 25 into 0.3 into pi, which is 3.14, again 2.5 divided by 9. So this I am multiplying using my calculator. So it comes out to be it's 25 into 0.3 multiplied by 3.14 multiplied by 2.5 divided by 9. It's 6.54. See, self-induction as inertia of electricity. See, what do you mean by inertia? Inertia means the property of body due to which it opposes any change in itself. You must have done inertia and laws of motion in class 11th and also in class 9th. Inertia is basically in class 11th, we define inertia as a property due to which body cannot change its state of rest or motion or direction. Like a body at rest cannot come in motion by itself. If you try to bring that body at rest into motion, that body will resist the change in state. That was inertia in mechanics, in laws of motion. Inertia of electricity means there is inherent property in a circuit due to which that circuit oppose any change in strength of current through itself. I'm talking about a circuit which has zero resistance. I'm talking about an ideal circuit, an absolutely ideal circuit, a circuit which have no resistance. Even this resistance less circuit will oppose any change in the strength of current through itself, not through resistance, but by through self-induction. So if you have a coil which have zero resistance, if some constant current is flowing through the coil, if current is 2 ampere, which is a constant current, then this coil will not work. This coil, if constant current is passing through coil, then coil will not, or you can say that then self-induction of coil will not come into play. The self-induction will play its role only if current changes. So if in this coil, say your current is increasing, this is R equal to 0. If this current is increasing, then self-induction will try to oppose this increase in the current. If current in coil increases, then self-induction will try to decrease it. Because it always opposes change in current. It's not resistance, it's else than resistance and new property for it. Again, if I take another coil having zero resistance, but now the current is decreasing. So can you tell me if current is decreasing, then how self-induction will oppose this decrease? It will further decrease the current or it will try to increase the current? If current in coil is decreasing, it's not increasing. Then self-induction will try to increase it. So in both the cases, you can see that there is something in the coil which is opposing the change in current in the coil. And that something which is opposing the change in current in the coil is self-induction. So it's not resistance. You're getting an obstruction. You're getting an opposition in the flow of current, but without resistance. This is known as self-induction, which is basically inertia of electricity. It plays almost the same role as the mass plays in motion in your laws of motion. That's a mass which opposes the change in state of a body. If you try to bring a body from rest to motion in mechanics, then its mass will oppose that change in state. So just like mass in your laws of motion, here this self-induction will oppose the change in strength of current through itself. So inductor is a new circuit element for you. Till now, we have used three circuit elements basically. First of all, we did capacitor, then we have used resistors, and we have also used cell. So we have used three circuit elements: capacitor, resistor, and cell. There is another circuit element, inductor. See how we can make an inductor. Inductor consists of number of turns of an insulated wire. It's basically the turns of a wire. If you take turns of a wire, that is an inductor. You take a wire, takes few turns of the wire, this is an inductor. Even if you take a single turn, it's an inductor, but a very weak inductor. Its inductance is very low. Inductance is low means it will offer very small obstruction in the flow of current. So this is the symbol of inductor. So inductor consists of number of turns of wire. So the way that for capacitor, we use a term capacitance to show the strength of the capacitor. For resistor, we use resistance. For inductor, we use this L, which is self-inductance, coefficient of self-inductance. So inductor consists of number of turns of a wire. So this is a circuit element which is just consists of number of turns in a wire. If I am saying that my inductor is ideal, ideal inductor means it will offer no resistance. The resistance of the inductor is zero. It's make of ideal wire having zero resistance. So ideal inductor have zero resistance. Next, the principle on which inductor acts on self-induction, that whenever current through an inductor change, then EMF is induced in the inductor, which will try to oppose the change in current. So it works on principle of self-induction. That's whenever current in an inductor change, then EMF is induced in the inductor, which oppose any further change in the current. That's self-induction. So the working equation for inductor is this: E is minus L di over dt. This is the working equation for inductor. The way we use Ohm's law for resistor, we use this relation for capacitor, we use this equation for inductor, minus L di over dt. Energy stored in inductor. So in inductor, energy is stored in the form of magnetic field. Say you have this inductor. So if I connect this inductor through a cell, key is open. So as soon as I close this key, current in the inductor will try to increase. This inductor will provide an opposition in the flow of current. So if current in the circuit increases, inductor will try to oppose this increase in current by inducing a current in itself. So this cell have to do some work done against this opposition. If cell wants to store a definite some I amount of current in the circuit, then this cell will have to do some work against the opposition offered by inductor. And the work done by the cell in storing some I current in the circuit gets stored in the inductor in the form of potential energy, which is basically energy stored in inductor. This energy is magnetic in nature. So work done by the cell to increase current from 0 to I gets stored in it in the form of potential energy. So whatever the work this cell do, that work then gets stored in the inductor in the form of potential energy. This is it. So you just have to calculate the work done by the cell and the work done to increase current from 0 to I against self-induction. Against self-induction. Gets stored in the system in the form of potential energy. That energy we have to calculate. So as soon as you switch the key close, the EMF induced in the inductor, EMF induced in the inductor, I have given enough detail. Okay, now you start telling me. Fatma, how much is the induced EMF in the inductor?
Minus L.
Yes, minus L.
Delta I by delta T.
So this is the EMF induced in the inductor. It's minus of L di over dt. Now, at any instant t, current in the circuit is I. The current flowing in the circuit is I. So this current I is basically greater than the zero current, the initial current, but it is less than the final current. So this I is the maximum current in the circuit. So it's this I is in between the zero and the maximum value. There is one current I. So now you have EMF. At that instant, the EMF induced in the inductor is this. The current in the circuit is this. Can you tell me the power supplied by cell? Does anyone remember the formula of power? So power is E multiplied by I. And do one more thing, like take this I as small I. This I is small I. This is equation number 2. This is the power. So if I substitute the value of E here, and in fact I'm using just the magnitude of E. This negative sign will give the direction. I need just magnitude of E. If I substitute the magnitude, it comes out to be power is L di over dt into I. That's equation number 3. So this is the power energy per unit time supplied by the cell when this current I is flowing through the circuit. Yeah, work done upon time. Good. So power is dW over dt, where dW is work done by cell in time dt. So in small interval of time dt, the work done by the cell is dW. So instead of P, you can substitute, I call this as equation number 4. If I substitute 4 and 3, I will get dW over dt is L I di over dt. I just interchange the positions. I'm writing I di. So this dt will cancel this. So this dW comes out to be Li di. This is dW, which is Lid. So to change current by an amount di, the work that needed to be done is dW. dW is work done by cell to change current by di. Okay, tell me, if the current is not changing, if the current is constant, then what would be the work done by cell? If I'm saying the current through the inductor is constant, the fixed current is passing through the inductor. Very good, Jubaina. Fatma, your answer? If a constant current is flowing through the cell, then what would be the work done by the cell? Fatma. See, it would be zero. Cell do work only when the current is changing. Because self-induction will play its role only if your current is variable. But if your current is constant, then cell will not play any role. Cell will not do any work. So if I say that current becomes constant, then work done by the cell will become constant. Cell will do only work done just to change current. So this is the work done by the cell to change current by di. But I need work done. Fatma, what is the initial and the final value of the current? Fatma, first, initial and the final value of current.
Sir, I don't know.
You don't know. Just look at the circuit. Look at the diagram that we have drawn. I must have written something below the cell. Okay, what's the value of current if your circuit is open? Yes, Fatma, if your circuit is open initially, how much is current? 0. Finally, so from 0 to a final value, that is I. So this is work done for small element, small change in current di. For 0 to I, you have to integrate it. This is 0 to I. This is Li di. So your L is constant. This is 0 to I. It's di. I di. Okay, tell me the integral of I. What's the integral of I here? It's I to the power 1 plus 1 divided by 1 plus 1. Yes, remember, from 0 to I. So work done is equal to L. It's I square by 2. Limit is 0 to I. The next step, you can take this 2 outside. So work done is L by 2. So it's I square minus 0 square. So the work done comes out to be half Li square. So this is the work done by the cell in increasing the current from 0 to I value. Okay, once this current reaches to its maximum value, then self-induction will stop playing its role. Cell will not do any further work done. Now this work done by the cell, since there is no resistance in the circuit, so no part of this work done will be wasted in the form of heat. The whole of work done gets stored in the form of magnetic energy. This work done, this work done will get stored in form of magnetic energy. This work done will get stored in the form of magnetic energy. So you can say the energy stored in the inductor U is it's half L I square. So is it clear? This is the energy stored in the inductor. Does anyone of you remember the formula of energy stored in capacitor? It was half CV square, right? Just like half CV square, this is half Li square. So after this energy in capacitor, if you can remember, we did a question on energy density of capacitor. Just like energy density of capacitor, you can get a question on energy density of inductor. Calculate energy density for inductor. When I say energy density, then energy density means energy divided by volume. If I say energy density, then energy density is energy divided by volume. So I take an inductor, or instead of inductor, just write this as solenoid. I take a solenoid. The length of the solenoid is L. The radius of the solenoid is R. The energy density means energy density of solenoid means, I take this as small u, representing it by small u, is energy stored in solenoid divided by the volume of solenoid. So I represent energy density as small u. Energy stored is half Li square divided by volume of solenoid. Volume is, I can write this as pi r square into L. For solenoid, we know that L is mu naught pi r square n square L. So I can substitute its value here. So the expression of your energy density comes out to be, this is 1 by 2. Instead of this L, I'm writing this term. So this comes out to be mu naught pi r square n square L multiplied by I square divided by pi r square. So this pi r square will get cancelled out with this pi r square. This L will cancel this L, and we are left with just its half mu naught n square I square. I call this as equation number 1. Next, you're supposed to convert this expression in terms of magnetic field. Magnetic field of solenoid. We have used this expression many times yesterday. The magnetic field of solenoid is mu naught Ni. That's equation number 2. So I can substitute this 2 in 1. When I substitute 2 in 1, you will get if I substitute this 2 in 1, you will get energy density is half mu naught n square. Say instead of I basically, not this is not 2, this is 2. I is B by mu naught. Current I is its B divided by mu naught. This is my equation number. If I substitute here instead of I, this will be B square by mu naught square into n square. This n square will cancel this n, mu naught will cancel the square. Energy density comes out to be B square by 2 mu naught. So this is the energy density of stored in a solenoid. Means energy per unit volume in solenoid. So if you see this expression very carefully, then energy density depends upon B, which is strength of magnetic field, 2 constant, mu naught, which depends upon the medium. So energy is basically stored in magnetic field. If you take a solenoid, then you have magnetic field inside the solenoid. So this energy is not in solenoid. This energy is basically in magnetic field. If you can create this magnetic field, if you can set up this magnetic field in any other place than solenoid, so if I generate some magnetic field in this room, then the portion of room which have magnetic field will have this much of energy. So this expression says that energy is stored in magnetic field. That energy is stored in magnetic field. Energy is not stored in solenoid. Energy is in magnetic field. If you take this magnetic field in any other place than solenoid, then too you will have the same expression. So this is expression of energy density. Is it clear? If you can remember, we have done a similar expression for energy density of electric fields, half epsilon naught E square. For electric field, this expression says that energy is stored in electric field, not in plates of capacitor. Similarly, this and this are same expressions. This says that magnetic energy density depends upon magnetic field. This says electric energy density depends only on electric field. So that is the energy stored in inductor. So after energy stored, we are left with just one last topic, which is known as eddy current. See, in eddy current, you will not get any numerical on eddy current. It's a very purely theoretical question. You can get some conceptual questions on eddy current. So see, what's the difference between eddy current and the current that induced current that we have discussed till now? The induced current that we have discussed till now will be induced only in a coil. For induced current, you need a closed coil or you need a proper circuit. For induced current, you need a proper circuit. If you have an open circuit, a circuit in this way, you can have induced EMF but not induced current. The induced current that we have discussed till now is possible only in a proper closed coil or in a proper closed circuit. But the type of current that we are dealing now, eddy current, this eddy current can exist in any conductor of any bulk piece of conductor. Means you need not have a pure coil. Instead of pure coil, if I take this mobile phone and say this mobile phone is of some metal, is of copper, mobile phone is of copper, then eddy current can exist in this mobile phone also. It's not a proper circuit, it's not a coil, it's not a closed coil, it's not a closed circuit. If this mobile phone is metallic, then you can have eddy current in this mobile phone. So that's the basic difference. For the induced current that we have discussed till now, you need a closed circuit, you need a proper coil. But for eddy current, you need a bulk piece of conductor. You can have a mobile, you can have a plate, you can have a piece of iron. And even in that piece of iron, you can get some eddy current. So can you tell me which one should be more common, eddy current or the induced current that we have discussed about the coil? Which one would be more common? Eddy current. Because we got eddy current in any piece of metal you have, you can have eddy current in that piece of metal. So eddy current says whenever magnetic flux linked with bulk piece of conductor change an EMF an EMF and hence a current is induced in it known as eddy current. So for eddy current, you should not have a proper coil or a proper circuit. You can have a bulk piece of conductor. You can have your plate. You have a plate of steel or iron. If somehow you change the magnetic flux associated with that plate of metal, that metallic plate, then that plate will have some induced EMF and hence induced current. That induced current is known as eddy current. For eddy current you can write as the ratio of EMF and resistance, or you can write this is 1 by R, EMF is minus of d phi over dt. So this is the formula of eddy current. That eddy current is, the formula is same as that of induced current that we did in Faraday's law of electromagnetic induction. But only the difference is the system in which you will have eddy current. For induced current, you need a proper coil or a proper closed circuit. But for eddy current, you need a bulk piece of conductor. It could be anything. You just need a piece of conductor. If you can change flux through that piece of conductor, then eddy current will be induced. Now, you won't get numericals based on eddy current. You will get two types of questions on eddy current. The first one is experimental demonstration of eddy current. You usually get theoretical questions of eddy current. That how would you demonstrate experimentally that the eddy current is in the system? Eddy current gets generated in the system. So there are plenty of experimental demonstration. I'm discussing just one of them. Experimental demonstration. Experimental demonstration for eddy current. So the experimental demonstration for eddy current says like I take two pieces of magnet. Let's assume that initially these pieces are not magnetic. There is no magnetic field here. And I take a plate. I take a plate here. It's a metallic plate. So for visualization, you can say that you have two some blocks. These are non-metallic blocks, and you take a metallic plate. Say this is metallic plate, and this plate is oscillating in between the blocks. So when I don't switch on the magnetic field, the oscillation of the plate is purely undamped oscillation. It's oscillating freely in between these two pieces. These are two blocks. In between these two blocks, this plate is oscillating freely. There is no obstruction, there is no restriction on the motion of the plate. This will keep on oscillating free. But when I switched on the magnetic field, I make this block as North Pole, I make this one as South Pole, then a magnetic field will get established in between them. This is the magnetic field between. This magnetic field, now when you're moving this, when this plate is oscillating in between the magnetic field, now as soon as you switched on the magnetic field, the motion of this plate will get restricted. While moving into the magnetic field, this plate will get restricted. You will see, you will experience that this plate will stop in between. You will feel damping. Damping means it's not oscillating freely, it will stop in between. So earlier it was oscillating freely, but as soon as you switched on the magnetic field, this plate will damped. Its motion will get damped. It will stop in between the magnetic field. When it enters the magnetic field, then it will move freely. And when it moves out of the magnetic field, then again its motion gets restricted. Its motion gets damped. Damping means it will not move freely out of the magnetic field. While moving out of the magnetic field, it will stop in between. So are you getting the observations? Then we will see why is it happening. I'm repeating it again. When there was no magnetic field, this metallic piece was oscillating freely in between this. In between these two blocks, this piece was oscillating freely. But as soon as you switched on the magnetic field, the motion of this plate gets restricted. It enters a stopping. Its motion is restricted. While entering the magnetic field, it will stop in between. While moving out of the magnetic field, it will again stop in between. This is known as damping. Its motion will get damped. It's basically a laboratory thing. So if you take two magnetic pole pieces and you try to move a metallic plate in between, then the motion of that metallic plate is restricted. It will not move continuously, it will stop in between. And that restriction basically shows there is some eddy current in the plate. So a metallic plate oscillating between the magnetic poles will get damped due to eddy current. Now let's see why its motion is getting damped. Say take this pen as magnetic field and this is the plate. Now as soon as the plate enters the magnetic field, after this pen, magnetic field will start. As soon as this plate enters the magnetic field, the flux linked with the plate will increase. The flux is increasing due to the motion of this plate into the magnetic field. As the flux changes, a current is induced in this plate, and that induced current will oppose its motion. This induced current will try that this plate does not enters in the magnetic field. Induced current will try that this plate does not enters in the magnetic field. So this induced current will apply a force in the opposite direction. When this plate is trying to enter in the magnetic field, Then due to eddy current, a force will act on the plate which is in an opposite direction. So this force will not let this plate to enter in the magnetic field. So the restriction comes due to in this eddy current and Lenz's law. Okay, so that was about electromagnetic induction. So before winding or starting the next topic, let's discuss few more numericals, some general numericals on the whole of EMI. So the first question is, a rod of some length L this is the magnetic field. Magnetic field is inverse. This rod is rotating in this plane perpendicular to magnetic field with angular velocity omega. So rod is rotating in a plane which is perpendicular to magnetic field with an angular velocity omega. You need to calculate the EMF induced across the ends of the rod. You need EMF induced across the ends of the rod. So this problem can be solved through many methods. The easiest one is motional EMF. You know that motional EMF, induced EMF is minus of BLV. So, but for this thing, you should know the relation between linear and angular velocity. If a body is moving on a circular track with an angular velocity omega, the radius of the track is r, the tangential velocity is v, then linear velocity v is omega. This is linear velocity, which is tangential to the circular path. This is angular velocity multiplied by the radius of the path. So this is if this rod is rotating in a plane perpendicular to magnetic field with an angular velocity omega, then the linear velocity of the rod is this, the length of the rod is L. And this V for this point will be omega multiplied by the length of the rod. So okay, now tell me, if I take a portion of the rod over here, if I take this point on the rod and its separation from the center, I call this as R. I'm taking one point A and another point B. The rod is rotating with angular velocity omega. Tell me, will these 2 points have same linear velocity or they will have different linear velocities? See, linear velocity is angular velocity multiplied by the radius of the path. For this point A, the center is O, the radius of path is L. So for point B, the linear velocity is omega multiplied by L. But if I am taking this point A, the center of the circle is this. The radius is not L, the radius is R now. So velocity of point A will be omega multiplied by R. So the linear velocity of each and every point of the rod will change. So we cannot calculate induced EMF in one step. For induced EMF, we will first consider a small portion of the rod. The length of the portion is dx. And let's say this dx is at a separation x from the center of the rod. Your induced EMF, motional EMF is BLV. We will first calculate induced EMF in this length dx. Then we will integrate it over the entire rod. So consider a small element of rod, of length dx and having angular velocity omega. And having angular velocity omega. So this is a small element dx. The angular velocity of this element dx is omega at a separation x from the center. Fatma, what's the linear velocity of this portion? What is the linear velocity of dx? The angular velocity of dx is omega. The separation from the center is given. How much is linear velocity? If this dx element, this is your dx element, this is the center of the circle, it's revolving like this, then this is the radius. That radius is x. It won't be dx omega, it will be omega into x. So the linear velocity of this portion is omega x. That's first equation. So EMF induced in dx
minus bx linear velocity.
minus BLV. But you won't use x. You will use the length of the element. Length of the element is not x. Length of the element is dx. So we have considered this element here. I'm calculating induced EMF in this element only. So it's minus b. The length of the element is dx. Its velocity is v. I can substitute 1 in 2. If I substitute 1 in 2, then we will get that induced EMF is minus of b dx into v. V is omega x. So the induced EMF comes out to be minus b omega x dx. That's induced EMF. And instead of writing its E, I'm writing d because this EMF is in small portion. D. This is d. But I don't need induced EMF in the small portion dx. I need induced EMF in the complete rod. EMF induce in rod. E. So can anyone tell me how to calculate the EMF induced in the complete rod? So for the complete rod, you can just integrate it minus b omega x dx from 0 to L. You can integrate it from 0 to L. You can integrate it over the entire rod. So this minus b and omega are constant. You are just left with 0 to L, it's x dx. So the induced EMF is minus of b omega. If I integrate this x, it comes out to be x square by 2. It's 0 to L. I can take this 2 outside. It's minus of b omega over 2. It's L square minus 0 square. So the induced EMF comes out to be, induced EMF is minus of b omega L square divided by 2. So this is the EMF induced across the ends of the rod, minus b omega L square. Just 2 more questions on the rotation of coil. Say instead of rod, I take this coil. The magnetic field is inwards. This is the center of the coil. There's one axis which is perpendicular to the plane of coil. The axis is parallel to magnetic field. And this coil is rotating about this axis with an angular velocity of omega. The circular coil is rotating with angular velocity omega, in a plane perpendicular to magnetic field about an axis parallel to field. Parallel to field. So it's not a rod. So you cannot use half BL square omega expression for this conductor. It's not a rod, it is coil. So here you have to use that Faraday's law of electromagnetic induction. So if A is the area of coil, then the flux is BA cos 0. Okay, now tell me, if this coil, when this coil rotates, is there any change in flux due to rotation of the coil? See, if this coil rotates, the angle should not change, it will remain constant. See, your axis, the perpendicular to the plane of coil is inverse. If I take this, I call this is my coil. So this is the axis perpendicular to the plane. If this coil is rotating like this, then the direction of axis is not changing. The direction of area vector is not changing. It's always perpendicular to the plane of the coil. Right? Your magnetic field is inverse. This is rotating in this way. The area vector will always be inverse. The direction is not changing. So your phi will remain constant. If your phi is constant, then what about the induced EMF? If phi is constant, then how much is the induced EMF? Yeah. Induced EMF is minus of d phi over dt, which is equal to 0. Induced EMF will be 0. So in the same question, if this coil is not rotating about an axis parallel to field, in fact, this coil is rotating about diameter. This is the diameter. This is the diameter. The coil is rotating about this diameter. So this is the diameter. I place, this is the diameter along the y-axis, okay? This is the area vector. The coil is rotating in this way. Now, can you tell me whether the angle between the magnetic field and area vector is changing or not? Magnetic field is inwards. Initially, the area vector is this, then coil is rotating in this way. So angle will keep on changing. So you will write this as BA cos theta now. This is the flux, BA cos theta. For theta, you can use this term. Angular velocity is angular displacement divided by time. This is again, I'm using a formula from rotation. See, you must have done velocity is distance by time. In rotation, instead of velocity, we use angular velocity. Instead of displacement, we use angular displacement. Angular displacement basically angle by time. So I'm using it here. Angular velocity. This is angular velocity with which the coil rotates. You can write your theta as omega multiplied by t. This is equation 1. This is equation 2. So I can substitute 2 in 1. When I substitute 2 in 1, then your phi comes out to be, it's BA cos omega t. So that's your flux, which is BA cos omega t. Induced EMF would be minus of d phi over dt. It's minus of d over dt of BA cos omega t. So your induced EMF is minus of dA. It's d over dt of cos omega t. So that's minus of BA d over dt of cos omega t. So when I differentiate this cos omega t, this will be minus of omega into sine omega t. The derivative of cos is sine, but along with t, you have a constant omega. So this constant will come in the outside the derivative. So the induced EMF comes out to be its BA omega sine of omega t. That is the induced EMF, BA omega sine omega t. So if your coil is rotating about its diameter, then you will have some induced EMF, which is BA omega sine omega t. And from this equation, the next chapter AC will start. This is the last equation of this chapter of electromagnetic induction. We'll start AC from this equation only. So this is induced EMF. In the same question, he can even ask you to calculate the maximum value of induced EMF. Maximum value of induced EMF sine omega t is 1. For the EMF depends upon time. For maximum value, your sine omega t should be 1. If your sine omega t is 1, then you will get that E max is BA omega. E max is BA omega.